This is T.C. Reimer, one of my first students in this area. This is Salvador Baruza Lopez, who's working, as it says on there, pseudo-relativity of graphene. It's a very exciting field, and it's one that I don't know that much about, so we're going to be exploring that in this year that comes. And Edmund Harris from mathematics working in that same area. So without further ado, I'm going to go ahead and start this show. And TC is the one that put together the graphics that you're going to see that's available on the web. So the thing that I've put on your desk is a list of all URLs that could possibly reach the stuff that we're doing here today, and other stuff that we're pioneering in an attempt to clear the fog that I believe is the current understanding of relativity and quantum mechanics at the University of Arkansas in Fayetteville, but also the rest of the world. So the question is, can we clarify that and perhaps simplify it? In fact, the better question is, can we clarify by simplifying? That's the faith that all mathematicians and theoretical physicists have. They're atheists after that. The main thing that I want to make sure that is understood here is how really badly the Galilean relativity fails for light waves. And this is the most worried picture of Galileo I could find. And we're going to actually resurrect him in a beautiful way before we're done here. But I also want to make sense of this white light wave speed limit and what it really means, how absolutely extraordinary that is, and then try to make it less extraordinary by replacing Einstein's what I call pulse wave axiom with Ken Evenson's continuous wave axiom, and he is the person that's responsible for making this number without a plus or minus, because it's now a definition of the meter, which can be measured less precisely than time by, well, now it's almost 10 orders of magnitude. This metrology is actually very fascinating. In any case, here's the old guy, Uncle Al, and it's his pulse wave axiom that I say everyone kind of knows it. Bunch of trains going in all different directions and not seeing the speed of light with anything but the sea. And this is a showstopper intellectually. I always had problems with it until just very recently. As I taught the course, I'd make fun of it. I'd say this is a roadrunner axiom. Go back to Chuck Jones' cartoons of the coyote, and this is the allegory for light. No matter what the coyote does, no matter what crazy rocket-powered skateboard unicycle he buys, the roadrunner still goes meet, meet, same speed. And you see, the relativity of Galileo is that if I see a room full of people that I want to get moving, and they're kind of lazy, I can arrange that. I could get all of you to move 3 miles an hour in that direction by simply walking 3 miles an hour in this direction. Now all of you people are moving at 3 miles an hour. And the idea of Galileo is that I'm doing that not just to you, but every particle and thing in the universe. Except light, where it fails. No matter what speed I go this way, the thing is still going to be going c by me. That's extraordinary. And it's really a black eye on the theorists of all these years, that they don't try to make this clear. It just says, Uncle Al said it must be right. That's a religion. We're in science. We doubt everything, including what I'm saying today. Okay? We're always trying to beat up the axioms. That's our job as a theorist. So, this being the first example of cartoon physics that's right, something's got to be done. We've got to take this axiom apart and make it something that, well, this one is comforting in the sense that these pulse waves that we make now are very precisely knowing where they are. This thing really can locate where the wave, each pulse, is. But comfort is not what we're looking for. We're looking for truth. So what we're going to do is we're going to use what's called Occam's razor. And here's a guy that worked for the church and got very fed up with their dogma. And he's known for the philosophical, mathematical idea of beating up axioms. And here's the man whose wife will be coming for a seminar next Friday to be honoring him. He died in 2002 from Lou Gehrig's disease, but he is the one that caused the precision revolution that's responsible for computers really working well, for the GPS, for incredible spectroscopy, which is where I was working. It's an amazing piece of work that he did. And we have here a coherent wave, a continuous wave, a colored wave. The CW stands for a lot of things, cosine wave. Okay, I've taken out all the Fourier components here, crossed them out, and I just have one, a pure light that's being produced by a green laser, okay, like this one. Now this is nowhere near as pure as the stuff he made, but it's extremely pure compared to anything that Einstein could have conceived of. Now this is the idea, is that with this simpler axiom, that's the whole idea here, is that first of all, it's sort of Zen-like. It's locating where places where the wave is not. So we're going to be working with zeros of waves. We're going to be looking with the white lines on a wave on that thing over there. But the idea is that where it's not is very precisely indication and convenient indication of a space-time coordinate system. We're going to build that out of two lasers. But this is just one laser for each of these observers. And the main point is that now we have something that's vulnerable. Here the pulse is not vulnerable, but here it is. It changes color when you accelerate. So that's what we're after. We're after doing that. And the major objection to relativity in quantum theory is it's the only major theoretical development that starts with second order and quite mysterious effects. In other words, it loses the audience on the first page. So let's try doing first things first. And while we're at it, let's deal with this sucker. Okay? So here is the bookkeeping, which really is due to Fourier, but I call it the keyboard of the gods. And TC has just put up something that you can actually manipulate. This is stuff that's just sitting here on the screen, but the idea is this is a keyboard of the gods that can not only, when I push a key, get a frequency of what I want. That's a normal keyboard for mortals. But this one can also, by moving this way, picking different keys, I can change the wave number, the number of waves per meter. That's affecting the wavelength. So not only do I affect the frequency, but I also affect the wave number by picking different places. So this is the theater upon which we're going to sort of make a control panel that builds things happening in space and time. So this is a very prosaic way of describing what Fourier had in his mind, and it's going to give us relativity and quantum mechanics essentially for free. So the idea is that whatever is here is the inverse showing over here. So if I've got a frequency of 4/5, I'm going to have a period of 5/4 in time, a wave in time. Okay? And then on this axis right here, if the wave number is 3/2 here for this point that I've pressed, well, the wave is going to show up in space with a wave length of a reciprocal of 3/2, 2/3. So lambda is 1/kappa. Kappa is the wave number. It's named after, well, the K is from Kaiser, who is the man that has the unit of inverse centimeter named after him. Waves per centimeter is his invention. You've all heard of Hertz, who gives you the unit of frequency. And seconds, you've heard of that. And meters, you've heard of that. So space and time you're more familiar with. That's where everybody works. This is where you should work. This is where you can control what goes on out there. It's TC can show you by when he makes something that's very big over here, he's going to get something that's smaller over there, and so forth. You see, it squeezes inversely. Okay? And the whole idea is that once you've pressed this thing and hold it, you get a 1 CW, single continuous wave. And it goes everywhere. And for all time. And has a speed that's determined by the ratio of the wavelength to the period. That is, distance over time is wavelength over period. So that, that particular slope of that line, in fact, the wave speed equals the slope to vertical of this thing. Lambda over tau, distance over time. Okay. Meanwhile, this thing here is sort of a flip of that. Everything's flipped when you go from these two. This wave speed is nu over k. That's the frequency number per seconds and number per meter. Well, it's going to be meters per second. That's the speed that you're getting by this slope right here. Now, this is an easy one to look at. When the slope is pretty close to zero, as I bring this thing down, what you get is something that isn't going anywhere. Over here, it's just staying still as time goes on. If he puts it right on the 45-degree line, which is halfway between, there we go, right there. Okay, that's like light. That's the way we're going to be plotting. That's what's going on the screen to the right. So these are very important little formulas here. And there's something else that you should understand at this point before we go into the relativity is, where's quantum mechanics going to figure in this? Well, wave number is quantum number. That's how many waves, well, half waves actually. Usually you have systems like the electron have half a quanta. They're going to have a wave that looks like that in some kind of box. And then I can have integer, then half integer, then integer, you see. Here is an integer. That's one whole wave in the box. Wave number equal 1. Assuming that this distance is 1 meter, that's perfect. But that is the idea of this wave business, is that quantum mechanics and relativity are really the same subject. And we're going to play that role. Now, that's called first quantization. The second quantization has to do with the amplitude. When you're over in that control panel, how hard are you going to press? You're going to make a soft note or you're going to make a loud note, you see? Well, that's quantized too, and because there's a wave and the phase space of an oscillator, and that's what electromagnetic radiation is, so you have to quantize the oscillator, something physicists are really good at. It's the only problem they can solve. Okay. Now, we need to understand why the velocity of light is fixed at that 45 degrees, but we'll get to that. If it is, we would like to take advantage of not having to write that number every time. As much as I like Ken, you know, it gets tiring writing 9 figures every time you're doing a calculation. So we're going to make it 1. And that means instead of lambda over time, we're going to lambda over c tau of dimensionless velocity. Okay, c tau is like length. C kappa, when we're working in a control panel, you see, that's like frequency. Okay? So get ready for that to happen. Also, we're going to put 2 pi on it at some point here. Anyway, here's the way we're going to work with. Most of the time, it's a beautiful blue-green. This is kind of yellow compared to what this is. This looks like the Caribbean, if we could color it correctly. 600 terahertz, half a micron wavelength. Okay? There's a half a micron right there. And that whole graph that's going on the board over there has got 1 micron of length. That's 1/1,000,000th of a meter from one side to the other. And I got 2 waves in there, so we're going to have 2 units. I should say the unit where you're going to be 600 terahertz when we talk about frequency. There's a 600 terahertz right there. And we're going to also talk about 300 terahertz, and we're going to talk about 1200 terahertz. Factors of 2 are going to figure in this discussion. Anyway, there's the whole wave going through time, just like that space movie is this. So this is a movie in a sense of the motion. Now notice my little rainbow, which is actual visible region. We're using false coloring here. I've got the UV and the high energy stuff, and then the low energy stuff, and the low frequency stuff down. Well, this is flipped over, obviously, because it's in reciprocal space, you see. The rainbow is flipped over. Okay, so next stop here is 1200. We're going to use this guy a lot. He's very kinky. That's what kappa or K represents, a pretty high wave number because his wavelength is very short, but his vector here that represents the wave number is huge, and the frequency is huge. 1200 is a very burning ultraviolet, well outside of the visible region. Below it here, above it there. And then infrared. That's what 300 terahertz is. 300 terahertz has a full micron of wavelength, twice as much as the visible green. So just to get you familiar with these diagrams, I'm showing you this real quick. And he's got a 1 micron wave now running on the board there, the screen there. And if I turn it around, that is, put a negative kappa, kappa can be negative easily, that just means the wave's going the other way. So we're going to be having actually that wave go in the opposite direction like that, and run into that powerful UV lamp. But we're getting ahead of the story here. We still have some work to do to discuss the bookkeeping that's needed to pull this off. Okay, part of the thing that we need here is Christian Doppler's notion that if you have a wave going in space, you can go with it, and if you do that, as time goes on, you see you're going to cross the crest less often. Here I've already, if I was standing still, I would have been hit by a crest or a zero or whatever of the wave at that time. But I have to wait a little time in order for to go, if I'm going with the wave. And obviously if I go closer and closer to speed of light, it's really going to take a long time before I actually have a wave seem to pass me. Now that's a kind of a, sounds contradictory to the Einstein pulse axiom or any kind of axiom, but we're going to make sense of that shortly. Going the other way, going the other way, if I go the other way, you see, I'm getting hit, and then I have to wait to get hit with the green if I'm standing still, hit. You see, I'm getting hit, I'm running across it a lot faster. Okay? So this is a Doppler blue shift if you're going into the wave. It's a Doppler red shift if you're going away, just to make sure you're familiar with that notation. Now here's a real philosophical question about light and its properties, its dynamic properties. Here are the characters of our little play today. Quantum opticians, quantum optics people, like to talk about light going from A to B to C, and they got tired of A, B, and C, so it's too impersonal, so inhuman. So they assigned A to Alice, B is called Bob, and C, well, they didn't get to that yet, but I call it Carla. Okay, they mostly just do two-level systems, so they don't need another person. But I do. I need lots of people. Anyway, I got Alice going here. She's the head of this outfit here, and Bob's sort of the assistant. So this is the, we're going against the usual political correctness here, but or with it. She's going to ask a very troubling question when Bob here reports he's seeing 600 terahertz and her laser is only 300. She's got an infrared laser and he's getting this beautiful green. Okay, so she says, well, what is its wavelength, Bob? He's giving the time part of it, but what about the space part of it? Okay, how long is that wave? Okay, so that's a really important question, which I discovered the whole faculty of the University of Rochester, which is optics, had not thought of. So can Bob tell that this is a phony 600 terahertz? That's the question. And the only other thing he's got to measure is wavelength. Okay? So that's question one. Question two, if so, what is the phony lambda? All right, we've got to answer that. Okay? So Alice is asking a very probing question here. So we're going to check it out in per space time, the control panel. Okay? with frequency versus the wave number, which is inverse wavelength. Okay? So, you know, here's a scale, 1 micron here, 0.5 microns here, 0.33 microns, that's the inverse. Here's the actual scale of the thing. 1 million waves per meter, 2 million waves per meter, 3 million waves per meter. Okay? So, well, which one of these is it? I know it's 600 terahertz. That's what my time thing, my very accurate Ken Evenson measuring device tells me. But what about that wavelength? Is it A, B, C, or D, or something else? Okay? How about being the wavelength of that actual laser, maybe? That's a possibility, isn't it? Well, no, it isn't. The answer to question 2 is C. There's only one kind of green. The alternative is there's an infinite number of kinds of green. The vacuum simply can't go but one kind of mode for each frequency. So, if he sees green, he measures half a micron, even though it's coming from God knows where. It doesn't matter where it came from. And that's the real point here, is the answer to question 1 is no. CW light carries no birth certificate. Kind of like the Republicans think the president. Okay? This is smart, that's stupid. Okay. So, this is the main thing that's making everything happen for us in the theoretical region. We're using Evenson's axiom and really proving it. If you need more proof, look at the sky. If bluer waves are even 0.1% faster or slower than redder ones, then each flash from a 5 billion year light year distant galaxy shows up dispersed over 5 million years. It would be a psychedelic light show out there, but no astronomy.
Yep, here's a pulse.
And there is a dispersing pulse where the colors are going different speeds. Whereas, and now put back if you can, the movie of the way light really is, with all colors marching in lockstep. This proves Einstein's axiom as a theorem. That's progress intellectually. Is to be able to prove something that is a crazy axiom and make it a theorem, or disprove it. We've done the former. Okay? Now, we're going to get these guys all lined up here. We're going to have Alice with her 600 terahertz laser, and that'll be true for the rest of the talk here. We're going to have Bob moving one way or the other relative to Alice. We'll take Bob's point of view finally, but right now Bob is seeing 1200 terahertz coming out of the 600 at the speed that he was going before. And the Bob-Alice Doppler ratio, or the Carla-Alice Doppler ratio, that's something we need to define. And not only that, but we need to do something with this number because it's going to be huge for things in high energy physics. We need to do something with this. B over A, Bob over Alice. Doesn't sound very good, but okay. Anyway, this fraction of new Bob over new Alice, 1200 over 600, that's the receiver over the source. We're going to find a ratio, receiver over source. Then we're going to take the logarithm of it for reasons that you'll be apparent, right? And Carla is the same way, okay? This is new Carla over new Alice. So they have two frequencies. Well, what if you know this, how do you calculate what these two would see if they shine lasers at each other, which in fact you could imagine they are, because he can just pass on Alice's beam to Carla, okay? So that's one of the things we're going to do. But let me advertise rapidity, logarithm of this thing, as very convenient. Let's take a 1 TeV, trillion electron volt proton in the Hadron Collider, or the one at Batavia. They could just barely make that in Batavia, and then the Europeans beat them by a factor of 10. Okay, now, the velocity for that is, not C quite, but pretty close, 0.9999. You've got 5 nines here, and then you've got the significant digits of C. This is a pain in the ass to have to do arithmetic with a thing like that. The Doppler ship is much better. It's 2,000 roughly. Okay, that's better. But the logarithm of that is even better. This is really indicating that the Hadron Collider is now operating at its binging part at about 7 to 6 times the speed of light in Galilean's way of looking at things. The Galileo way of looking at things. So this is a number you can work with, you can think about it. And then when you're talking about low velocity, rapidity is nothing but U over C. We'll see that coming up later. So I really advertise this parameter as an important thing. Now let me show you something else that makes it important. And that is when I look at the log of 2 to 1 for Bob over Alice, or the log of 2/3 for Carla over Alice, I notice a 0.69 here and a minus whenever you have a number less than 1, or whenever you time reverse. And this is one other axiom I need to build all of modern physics. I need Evenson's axiom, but I also need time reversal. Time reversal has to be where we switch receiver and source. So we switch the thing here. I'm going to turn it into a 1/2, and the log of that is minus 0.69 instead of plus 0.69. So this is time reversal, okay? Time reversed is this of that. That's a really key group theoretical concept, and this is a group theoretical thing. Group theory is nothing but grown-up geometry, but you got to do the geometry right first. So here's Carla-Bob dipole ratio, okay? That's what we were asking for before, okay? All I have to do to get Carla and Bob is slip in Alice between them. I can go nu C over nu B equal nu C over A times nu A over nu B. Bingo. All right? And not only that, but if I'm going to write the amplitudes as exponentials, as boom-boom functions, okay, exponential functions, then I notice that the Carla-Bob rapidity is just a sum of the Carla-Alice and the Alice-Bob rapidities. In other words, Galileo gets his revenge. This is part 1 of his revenge. Okay? Rapidity adds just like Galilean velocity. Wow, is that convenient? Or what? So this is the parameter you need for the Lorentz group, if you know your group theory. That's what we're aiming at, is to understand that thing. And all the people who developed group theory admitted they did not understand the Lorentz group very clearly. So, we're going to let space and time tell us how to get at that geometry. We've already looked at 1CW in a very elementary way. I need to go a little farther with that. And I also need to get 2 CWs colliding with each other to make a coordinate system. So here is the laser sort of dissected and written in terms of what are called phase space, well, shall I say indicators, but this is called a phasor. Not to be confused by Star Trek phasors. But you'll see them running at the bottom of this screen and the bottom of that screen over there, here with a 1 micron wave and over there with a 1/2 micron wave. So we have the infrared 300 terahertz going here, which is what this is. And you see that what I have done is make a clock, and the clock has very convenient description in mathematical terms. And I've written this stuff on the board here. I've written the Euler identity, which is e to the IA is cosine A plus I sine A. Just out of curiosity, how many people got this in high school? 1, 2, from other countries, right? 1, 2, 3 from the United States. Anybody else? It used to be in junior year. We, look at the last election. We've sunk, okay? But this should not be wait for calculus for this, okay? And you should not have to wait for the hyperbolic one, which is the other one we're going to use. It's actually simpler. It doesn't use this crazy imaginary number, okay? But anyway, I'm going to have real versus imaginary. There's going to be the real wave, and there's going to be the imaginary wave, quarter wave apart, ahead. And that's just like American business. Reality is preceded by imagination by exactly 1/4. Unfortunately. Okay? Now, this blows up. I'm going to sort of skip this, but I call this the crazy thing theorem. if you have a crazy thing that squares to -1, then the exponential of that crazy thing times the parameter is the 1 times the cosine of the parameter plus the crazy thing times the sine of the parameter. And there's the crazy thing that we're using. There's the one we should be using because we need to take this out into 4 dimensions, and that's exactly what the doctor ordered when you use quaternions, which is a really crazy thing. It's I times the crazy thing. But Pauli didn't think they were crazy. They're called Pauli matrices. That's one of 3, and then there's a unit which makes 4. So he failed to give credit to Mr. Hamiltonian. To Mr. Hamilton, who invented this in 1840 or so. Now, what TC is showing here is a wave that can be animated, and there's the URL for that. This is our old website, our 2005 website, where we just got started on this, but now we've got a lot more, and you can use all of this stuff as you see fit. Now, I'd like to point out that in space and time, the way we look at this is a whole bunch of phasors. Now, when people refer to gauge, I always wonder what the hell, where's the gauge? I have a gas gauge in my car, I have a gauge in my furnace, I've got a gauge on a temperature. Where's the gauge? Where's the gauges? There's the gauges. These really are gauges. These are things that don't have an hour hand. The second hand doesn't have an hour hand, doesn't count for you. It only counts modulo 1 rotation. That's a gauge as opposed to a clock. But it behaves like a clock, and if we read it right, and that's what Evenson did, is he got something to count the damn thing, then you can play games with this thing. Now we have 2 extremes here. We have a set of clocks that are set up for whoever it is, I think it's Carla, that's got 300 terahertz laser, and according to her, they're not moving, but they are turning. Okay, their frequency is 300 terahertz, and their linear velocity is 0. That's one extreme. The other extreme is what we've got on this chart here. None of these phasors are turning. This phasor is frozen. This one's frozen at different times. The clock velocity is close to C, or right on C. I can make it 999999956 there, but whatever, it would just look the same with all those 9s. And the frequency here is 0. Superman has gone fast enough that he's frozen. Okay? So already we're seeing one of the most extraordinary things about relativity. That slowage of time, slowing to almost stopping for many things. So now we're going to go to town on this. Alice says, okay, Bob, we're going to hit you from both sides now. Carla says, look out, Bob. And Bob says, yikes. Here come 2 waves to run into each other. Okay? Now, this is something you learn in sophomore physics, but you don't quite learn it this way. Notice the phasors look different. There's an upside-down cycloid here and a right-side-up cycloid, like we've been looking at on those things, because this one's going this way, this one's going that way. So, what do you get when you put those 2 together? Wow, says Bob. Cool. You guys made me a space-time graph out of real zeros. And there's a picture of it happening. And this is really neat, because you can look at the real part of the wave, which is the dark blue, and you can see that every once in a while, bang, it's everywhere at once. Bang, it's everywhere at once. Bang, everywhere at once. You see, it's marking time, but laying out space. That's the x-axis. Meanwhile, the group thing is just going along, not moving at all, and making the vertical lines on this graph with its nodes. This is really cool, as Bob says. And the question is, how'd you do it? What happened? Okay, now as I say, that's sophomore physics, but let's do it in a way that's general enough we can derive all of relativity and quantum mechanics with it. I get zeros for any wave sum by doing what we've done in algebra since it was discovered by the Middle Easterners. And that is by factoring it. Well, here we're going to factor it into a phase and group part, because we're looking for zeros. Okay? So, remember your algebra and how the half sum plus a half difference gives you one of those terms, and a half sum minus a half difference gives you the other that's actually a group theoretical result, symmetry and antisymmetry. So presto, you factor the sum into two parts. Two parts. One of them, which, according to this result right here, gives you a cosine, actually 2 times the cosine. That's going to show up. But here's the geometrical picture of phasors adding, giving you half sums and half difference. So there's a geometry to it. And what's even more cool is that here's the relativistic geometry. I'm going to just say frequency A is moving, and B, I'm going to go to the frequency gauge that has B equals 0. And then I'll just see sitting there with a frequency of B just standing there, and A is going to rotate around it and make, a circle which has a Thales rectangle in it. So this is 600 BC we're talking about here. That no one wants to look at. They look at it this way, which is fine. But this is telling you that Galileo's Revenge Part 2, phasor angular momentum adds just like Galilean velocity again. Are you happy now? That's the happiest picture I could find. He wasn't very emotive. Right. Until the Pope gave him some shit. Then he was very emotive. Okay, so that's this deal here. This thing adds up to a group factor that is the cosine wave that you see surrounding the oscillation, the green thing here, and the guts of the wave. That's what we're after. That's the phase part of the wave. Okay? So that is really amazing, I think, and wonderfully beautiful. But what's it look like in the control panel? And this is what we're doing with the geometry here. In the control panel, we have what Bob has noticed is a baseball diamond. He says, okay, Bob, it looks like a baseball diamond with a P phase at pitcher's mound. That's convenient. P for pitcher's mound, P for phase. Okay? That's the half sum of these two, right and left. And Carl is also noting that the group guy, which is this thing minus this thing, over 2 is right here. So that's where, and this is Woody across the hall that I thank for thinking of that mnemonic. And a G for grandstand. That's where the grandstand of American baseball. So you see, I'm trying to design this to teach the Americans. Okay? Europeans, they suck this up very quickly. But Americans, they have trouble. So we do baseball. And over here, you see, Bob is noticing P and G vectors are scale models of the 0 grid that's getting here. So the control panel, which is, now we're pressing 2 keys, this one and this one. And these two happen, making the grid. All right? So that means all we have to do is do some Doppler shifting, and we've got relativity handed to us on a silver platter or a platinum platter, whatever you want. Like paper, I give it to you. Okay? So this is really, I think, a key idea. First of all, the mnemonic is being shown there. We go to first base, and that's where Alice is. And you say, no, Alice is over here, right? And Carol had made this mistake, so Alice is correcting her. She says, no, Carla, you're on third. I'm on first. My laser points right, yours points left, and that's what counts on a diagram like this. Okay, so here's the R plus L over 2, there's the R minus L over 2, they're respectively phase and group, and we're going to be working with that. Okay. Now I should point out, when you do a pulsed thing, and I think TC has one of those, this is really hard to do on a web, but there it is. You make a baseball diamond in space-time. And that's because you've got a whole bunch of Fourier components going at once that can make this pulse train. Now pulse trains are what's responsible for us measuring time to 1 part in 10 to the 18th. That's a less than a second in the life of the fucking universe. I mean, this is just absolutely unbelievable. And we're doing it because of Evenson's work. All right. So here's what we're going to have if Alice and Carla both are moving, this is Bob's viewpoint, toward him. Well, she's moving toward him, she's moving away. He's caught between them. lucky guy. Anyway, what we have is a very big blue shift and a reciprocally small red shift, that is 2 1/2 factors respectively. Okay? And Bob looks at this one and said, holy cow, that's UV. That's really bad UV. It'll burn you the heck out of your eyes and everything, actually. So Alice says, hey, yeah, I agree. It's pretty fierce for you. You better put on your sunglasses. So he says, yeah, puts on his sunglasses, just like he's told. Meanwhile, Carlos says, hey, my light's going to be a lot nicer on you. It's nice, warm infrared. It's not going to burn you at all. All right, so that's the situation we have. The question is, how fast do you have to go to do that? That's what we've already got written right here. When you do the sum and difference of those two, you're going to be getting, first of all, a new pitcher's mound. Pitcher's mound used to be here. Now it's here. Okay? So what we got is a baseball diamond with a marathon run to first base, a short steal to second, a marathon again, back to third base, and then a short steal home. If this is the baseball diamond actually the way it would be laid out. It's more like a perspective view in which the pitcher's mound and the grandstand, which is going to be coming up in just a minute, but here's the actual formulas, you see, using the exponentials to describe the Doppler shift. It's a sum of plus and minus here, and a difference up here, a difference because of this one having a negative in that first component. So we're playing with these functions right here now, cosh and sinh instead of cosine and sine. And that's really cool because that is the theory of relativity right there, the whole damn thing. Okay, it's just summarized right by these two equations. This one's sine, sinh I'll call it, and cosh, and then this is cosh and sinh. And that's making this graph. And I guess we should show that because it's really quite an amazing piece of wave work. And there you see it going from the ultraviolet on one side, the infrared on the other side, and it's making a very strange space-time thing. Now that strange space-time thing is called Minkowski graph. Dr. Hermann Minkowski, a math teacher for Einstein. And Einstein was sort of a slob in his class, so Minkowski said, you're a fat, lazy dog. And a Polish does not say that to a German. So Einstein would have nothing to do with Minkowski when he became famous and did relativity. Minkowski sent him a letter showing, hey, you can draw a graph of your transformation. And people will understand it. Either Einstein wanted to be an obscurantist or he just hated Minkowski. I don't know which. But that's the thing. Now you see the real part here is cutting on the now line the lines that go this way. They used to go infinitely fast. They are now just faster than light, which is really something we're going to talk about very shortly here. Okay, so this is really quite extraordinary, and I think he has a better shot of that that's blown up. There you go. And he's going to set it so you trace the zeros. And you see the arrows there indicating who's making these x-axis. This is Alice's x-axis according to Bob. And that means that every moment, when he goes on this side of the thing, he sees her into her past. When he goes on this side of it, he sees into her future. And he also sees that she's got short lengths, shorter than she should. And she's got exaggerated time distances. That's called time dilation. We'll mention all that. But what really comes up here is we got to measure this sucker. We got to have numbers for everything that happens in this thing. We got to count where the waves cross the axis, what the slope is, all kinds of stuff. So that's what the next 15 slides are going to be, is slowly filling a table of all the stuff you need to do relativistic quantum field theory. The parameters for it are all sitting there waiting to be used. First of all, waiting to be noticed at all. So we start with the things that, out of which they're always made, and that's the blue Doppler and its reciprocal, the red Doppler. That's the Evenson idea attached to a time reversal. They have to be reciprocals of each other. So let's look at the phase frequency. Okay? that is plotted right here. Okay, this is frequency. The pitcher's mound has a vertical coordinate of new phase, which is 5/4, 1.25. Okay? So that's new phase of Bob over what Alice has as her number, 600 terahertz in this case. Okay? Next stop, phase period. How long is it before one of these phase waves crosses any of the axes you might set up? So there is a period, according to Bob. That's what the prime means, Bob's prime beef or something. Anyway, we've got tau prime phase equal tau Alice times seek, hyperbolic seek. The hyperbolic seek is 4/5 in this case. Now, everything on this table on this side is going to be reciprocal of everything on the other side. That's the center of the table right there. So they are self-inverse, these two quantities. And they have a very famous, both of them a famous name. But the rest of the table is where the action is. And that's what I want to show here. Phase wave number. Phase wave number. Okay? The kappa is 0.75, 3/4. Okay? And then its partner in crime, the lambda, this thing that's measured over here, that's the distance between these blue lines crossing on the horizontal axis of Bob. Okay? And what you notice is the ratio of those two. Remember, that's the velocity. This is the p slope. Okay? This is v phase over c. It is always faster than light. Its speed limit of light is from the high side. It can go infinitely fast. You saw it doing that. But it can go any phase down to c. This is what the guts, the heartbeat of nature is. It's the phase, the gauge of everything that we know. So we're really talking about something pretty deep. Now let's go and do the group. That's the other lines that are going slower than light. They're more sedate, more used to, more classical. These are the things that Newton actually was measuring. He knew nothing about that other stuff. He knew nothing about the inside, the story. Okay? So here's the frequency group. Okay? The grandstand vector, 0.75. That's 3/4. Okay? And then flipping over that to 4/3, that's tau group. Remember, they're reciprocal, frequency and the period are frequencies. Those tau groups are pretty sizable, 1.33, 4/3. Okay? And here's its name, cosecant. The one on the other side is a sine hyperbolic, sinh. This has got to be the inverse, cosinch. Cosinch. I don't know how to pronounce it. I'm not from Lithuania, so I can't do it. Anyway, there is the other thing about the group, the wave number for the group wave, okay? 5/4, 1.25. Okay, we can see it easily here. It's difficult to see it there, but not impossible. You should get used to doing that. But this one I can easily see. This is the lambda living in the wavelength. It is 4/5, the reciprocal of 5/4. So this is the kosh, and this is the seek. I can say that one pretty well. You sound like I'm from the Iraqi parts of the world. Anyway, there you're doing the measurement. We're almost finished with this table, but we have to point out that this is the classical velocity. This is the group velocity, the thing we can actually see. We have a horrible time, in fact I'd say impossible time, getting at that heartbeat, but we can measure this one because that's the classical motion that this thing is trying to put upon us. Okay? And this one is a tangent hyperbolic. It's the ratio of the sine hyperbolic to the cosh hyperbolic. 3/4 over 5/4 is 3/5. That is how fast you have to go to get a double Doppler. 3/5 the speed of light. We've just figured that out just by ruler and compass, really, with diagrams like on the board here. So there is that slope that we're talking about measured off over there by looking at the ratio. All right. Well, here's the whole sort of story wrapped up in one big fat table. basically 16 terms that are very intertwined. That is, a lot of things are very equal. And what I've got here is just decomposing the two group and pitcher mounds in terms of the original Alice group and pitcher mound that we had where a baseball line wasn't all warped. And these two numbers that come popping up here, hyperbolic sine, hyperbolic cosine, are the Lorentz representation matrix components. And we are going to be talking about them a lot, but I should point out that the first two numbers and the old-fashioned notation for them in terms of beta, which is U over C, that's called the relativity parameter. Bullshit, it's not the relativity parameter. Rapidity is. That's a terrible parameter. Giving you a point 99999999999. You think it's, you're running for president in the last election. Okay, now this is the two most famous numbers in the table. They're right in the center. The Einstein time dilation, which makes you have really long times, okay, if you're somebody sees you moving by, or short lengths. You look real shriveled up a little bit, you see, and that is, I think, you know, something we have to discuss. I will take this one on a little bit if we have time here. But given that we only have about 20 minutes, I think I will speed ahead. And I want to take this diagram that has the new pitcher's mound, and then it has a new grandstand over here, okay? But I want to look at it in terms of that little phaser geometry that I talked to you about before. This is back to 600 BC. The first man, an olive oil merchant who had some time on his hands and a wonderful place to live, was the first to predict an eclipse by geometry. Can you imagine how that's, I mean, that scared the shit out of me. They just, oh, whoa, get away from me. Right? Hatred involved, really. Okay? So, his theorem that he's known for, if you've taken a geometry class, is that the diameter always subtends a right angle. Well, it's just like that right angle of a rectangle that we saw in the phasor addition. Half sum and half difference are sitting here, but now it's frequency that we're reading, okay? We have here 4 units blue shift and a 1 unit red shift. So this is 1200 terahertz, that's just 300 terahertz, okay? You take the geometrical mean of that, and that will be the frequency of the laser that's making this. That's cool. I mean, this is where the geometry really shows for the relativity. Here is the difference mean, and here is the plus mean, what we would call the arithmetic mean, okay, of 1 and 4. That's the 5 halves, that is the Koch, and this is the cinch. Remember that they're half sum and half difference, respectively, of the Doppler shifts, you see. So that's the geometry of this thing as we have it written here, okay? And the ratio of those two is this line right here, and that has the slope 3/5. That's your group velocity, okay? Now, through all of that is a time reversal hyperbola. And the reason that's going through there is because when I distort this baseball diamond, I have to do it proportionally. If I go 2 times here, I got to go 1/2 here. I always have to have the inverse of these 2 Doppler shifts. So that's the time reversal axiom. The rest of it's Evenson. Stay on your baseline is what he says. Okay? So you end up what's called the Einstein invariant, Einstein-Lorentz invariant. And that's derived in all kinds of clumsy ways. This is just giving it to you. Okay, and so TC can show you what happens when you change, and you can play with these things. You can just grab those little bullet points there, start with a baseball diamond that's all lined up nicely, and warp the hell out of it. You just can keep going either direction and making the pitcher's mound and the grandstand get closer and closer together. And then you can click on things that will make a coordinate system at any one of those points that goes with that. It's not shown right here, but we're going to be looking at it later on. Okay, so there's the group thing being shown, which he has running there as well. There he's got the actual Minkowski graph in the background, sort of faintly there if you can see it. So that's the thing we're going to play with. Now, what I've got to do in just the last few minutes here is point out that the mainstream relativity has books like this, Taylor and Wheeler, or Wheeler, Meissner, and Thorne for a full gravity theory. That's the sort of the mainstream, and the one that I learned from. But then I discovered, because I was so frustrated with the fact that they didn't have any axioms that were worth a damn, there comes this crazy thing by not Einstein, but Epstein. Okay, anybody seen this book? Well, no, you haven't, because he had to publish it himself. His father gave him some money, bought a printing shop, and that's what where these books come from. Okay, it's $14.95 on Amazon. Okay, he takes a whole different view of relativity. Now, what's interesting, I invited him to come and talk here 10 years ago. He's a nice guy. He worked at San Francisco City College, and that's the feeder school for Berkeley. If you're having trouble getting Berkeley, you go there for a while, and you can get Berkeley in physics and math and chemistry, all kinds of things. So this is the relativity you would get if you were at there. Now, these are my diagrams here. I had to, clean up what he had done a little bit, and then, I already really had this. It just I didn't see, make it important, and that's what he did. And he's done it in German and other things since then. He's actually pretty close, as far as I can tell, to sort of an Alzheimer's state. But the work lives on, and the idea is we've been looking at light head on. He's looking at light coming perpendicular. And when I said that speed of light is really constant, I said speed only, not vector velocity. So vector velocity does change, but the speed doesn't. So you get this geometry. It's really cool. It has an angle called the stellar aberration angle. Astronomers knew about this for long before relativity was discovered. So it's the other parameter besides rho, and I'm relating them right here, and that's what we need to do. Now his relativity is described in a very strange way. He says, don't worry about the fact that you can't go the speed of light. You are. He says everything is going the speed of light through proper time, which is given by this hyperbolic relation, and space. So he pulls this trick. This is a really incredible trick. I'm saying trick is to take the hyperbolic form of the proper time, which is what we've been deriving here, really, into a circular form by just switching the terms. So he gets a Pythagorean relation that involves a circle. So his thing is, you say, okay, if you stand still, you're going the speed of light through proper time. That's your aging. But if you take some high speed, you won't age as much. You'll use some of your age to go somewhere. Okay? In other words, if you jog a lot, you're not going to die as soon. Now, you have to really jog 3/5 the speed of light. Okay? I'm not up to that yet. But the idea is that all of the things that we've been talking about, length contraction and time dilation, have a sigma relationship involving ordinary circular functions. And that is cool. And TC will bring up a thing that makes sense out of that. And I tried to show him this, and he has a part in his book where at the very end on one page he tries to describe the hyperbolic stuff and does a terrible job of it. He didn't understand that part. He just had this, in his mind. That's not the way to be. You try to bust your way through to everything you can possibly find. But anyway, just taking as our main functions the secant. Well, first the sine. Everyone's heard of the sine, right? Okay? I'm not drawing the cosine, but I'm drawing the inverse of the cosine, which is the secant, the piercer, the sword. This is slope of incline. Okay, that's some pretty name comes. Then tangent is appropriately named. It's the distance of the tangent to projection to the secant. Okay? And here's the normal way you draw the tangent to get a relationship. And you take it over here, and you get a part of a hyperbola. Okay? Now the thing that's cool about this is that the rho is the area subtended by the hyperbola, the whole area to both branches. You got to count this side too. There's another hyperbola over here that's facing this one. Okay? So here we have the hyperbolic tangent replacing what was the sine of the sigma angle, and here we have this hyperbolic sine replacing what was the tangent of the sigma angle. That's a wonderful sort of reciprocity that I have not seen discussed anywhere. It just sort of popped up in this interplay. There's another picture with the other functions. Okay, the cosine of sigma is equal to the inverse cosine of rho, and so forth. We'll put all these things in a table and show you. But I think you can look at TC's thing as he runs this thing, and you can see that the sine of sigma is the tangent hyperbolic of rho. The tangent of sigma is the sine hyperbolic. That starts us off. Then the sec of sigma is the hyperbolic cosh, and the cosine of sigma is the hyperbolic secant there. And then finally, cotan and cosecant play that little reciprocity game as well. Okay? And there they all are. Now, what good is that? Well, that is where you learn what mass is in mechanics. And you learn it exactly relativistically. And that's what I want to do right now. But I should point out that we've taken this mess and made what I call Occam's sword out of it. And this is the geometry you should look for in every possible relativistic situation that you encounter. You will see that in there, and then you can figure out what's going on. It's really a wonderful roadmap to an otherwise forest of possibilities. Okay? So these 12 wave parameters, or 16 depending on how you count, are all sitting here right now with the sigmas taking over from the rhos, just like, you know, nothing had happened. So what is their role? What's the difference between those two? And that's what I really want to show in just the last 10 minutes here. This is going to be rather spooky. Okay, are you ready? I want to use these parameters to show you what mechanics is. And this is mechanics of mass. Okay? Exact. Not that lousy Newton stuff. Okay? So, here's what we're going to do. We're going to go down to Newton's speed level, and we're going to say, what do I get for one of these? Namely, this guy right here. He's an important one. That's the time dilation one for Einstein. But there's another one that I also have to do, so I'm really going to use the two coefficients that go in the Lorentz transformation, and that's what makes the sense of this. Okay? So, I'm going to use nu phase, and I'm going to use kappa phase. I'm going to use the wave number of the phase and the frequency of the phase. Okay? And I'm just going to expand them to two terms for u much less than c. And remember, I told you that rho is u over c. That's easily seen on the next line here, where the hyperbolic tangent, the ratio of those two, is very close to rho, because tangent is just its own variable at low values. Okay? U much less than c, and that's where we work in this building. We don't challenge that at all. We're not nuclear physicists or high energy guys. But these are the power series that we're playing with here. Okay, and this B here is Alice's value, the base. Okay, not Bob, it's Alice in our allegory. All right, so let's build mechanics out of that. Okay, first of all, nu phase, if I were to go ahead here and use that u over c relationship, nu phase is the base of the hyperbola plus 1/2 of the base over c squared times velocity squared. That's what we get for it. And the kappa phase, this guy right here, well, sine of x is x, so that's just b rho, but that's b rho u over c, okay? And the u over c has an extra c to that one. And I took the c off of kappa. Remember, we had to scale that to make the slope of light 1. All right? So, that's kind of neat. It looks like Newton's kinetic energy and momentum. If m was that thing, and there it is again. You see, it's telling us m is that thing. M is that thing. It's shouting at us that m is that thing. Okay? So we're just going to go ahead and set m equal to a scale factor. That's what is going in here. Basically, we're attaching a scale factor so we match the units of this, what looks like a coincidence. Okay? And once we do that, okay, I get the new phase looking like this, and the kappa phase looking like that. Okay, the scale factor's there. All right? And that, of course, means that this HB is mc squared. So the bottom of the hyperbola, that there is the rest energy that Einstein was so famous for discovering. This is the formula, not that part of it, but anyway, E equal mc squared is written on practically every bathroom wall in the world somewhere. Okay, along with all the other graffiti. Okay, so we have to go ahead and write that, mc squared plus 1/2 mu squared, and this thing is h bar kappa phase equal mu. Okay. Now, question, is it lucky coincidences or a cheap trick? Well, maybe. That's the thing you have to question. Okay? So let's go ahead and try the exact value for new phase. Okay? So h nu. Now, there's a coincidence I called this scale factor h because we're getting two very famous results at the same time. The one in 1900 is Planck's result for energy equal h nu for vacuum state, hn nu for the excited state. That's what we're getting here and putting it together for relativity. This is Planck 1900, this is Einstein 1905. If you use the old-fashioned formula, instead of Koch, use that. Okay? Wow. That's nice, huh? You don't have to wait for the Hadron Collider to give you a Higgs boson to understand what mass is. It's right in front of your face. Now, 21 years, 1921, 16 years later, after the 1900 Planck thing, we begin to get some relations involving the other contender in this, the one that's looking like momentum in the Newton regime. Okay? Well, I'm going to pull this guy out and change him a little bit, and bingo! De Broglie, 1921. They finally figured out that if they wrote an h bar k, that's the angular units, is equal to momentum is equal to that. And Einstein already had that part of it, but he didn't have the wave part of it very well. Waves, like Einstein had trouble with waves just as badly as Newton did. So this is really the whole picture that we're getting here because we're only looking at the top part. The bottom part where the phasors go backwards, where the gauge is negative, is really where the action is because that's a tremendous frequency jump for anything that weighs more than a neutrino. And we don't know what the neutrinos really have for a rest mass. But let's look at this just a minute. Definitions of mass that come out of this thing. First of all, this new thing called Einstein's rest mass. Now that's an invariant. No matter how fast I go, I'm going to see that for some particle that doesn't change, and that includes our box of light. Our box of light is going to be slightly heavier. Let's just say it'll have to be more massive. I haven't gone into gravitation here yet, but the momentum mass is the other side of the thing. This is defined by the ratio P over U. That's a classical Galilean almost Newtonian relationship. And we're going to stick in the new relativistic values, group velocity, and the momentum that we came up with there. And get a thing that looks like that. P over U is equal to momentum over group velocity. Okay? These are quantities that we just derived sort of sneakily from Newton's stuff. So here we go. That's the momentum mass. Now that's the correct formula for what people say is what everyone calls mass. But it's very misleading. It does have limiting cases of infinity. You're going up exponentially. All these things use the boom-boom function. This is geometric, so you're going to get stuff that blows up, including so that is just part of the story, what light is doing. But the effective mass is the one that's really queer. This is where I take the F over A, that's F equal ma is the Newton's law. Newton 2, I guess this is called, F equal ma, so F over A is his m, okay? And that's the rate of change of momentum with respect to velocity in the classical world. We're going to stick in that those two things, not just P over U, but dP, du, we're going to stick in to get a relationship. So that's what we have for dP. P was the hyperbolic sine, this is hyperbolic cosine as a derivative. The hyperbolic tangent derivative is the secant squared. Okay, and bingo, I get cosh cubed. This is the effective mass. Now, this isn't the way most people do it. Here's a more standard derivation of the effective mass using the same sort of calculus, but focusing on the kappa or k vector. Okay, you could replace this with nu and that with kappa if you want to get rid of the 2 pi's. But there it is. It's not the square root, but the cube of the square root down there. Now, how much mass does light have? This is, I think, really quite amazing. Okay, rest mass. Now that's 0. The light is the lines coming down, and the hyperbola is completely degenerate. Okay, so we don't argue with that though. The rest mass is 0. But momentum mass, it can be anything. It depends on what your kappa or nu is for the light. Okay, and remember that nu is kappa c. Okay. What's the effective mass? Infinite. Infinite. Well, of course it's infinite. Evenson axiom says you can't change the velocity. All right? Now, Newton, excuse me, I think I had, Newton used to complain about his corpuscles of light in his optics book, that it had fits, that it was going crazy. Oh, this is crazy. This is triple schizophrenia. Okay. Now, here's something else I want to show. We got about a minute here. I want to go through this real quick. If you guys are taking advanced mechanics, you have a thing called the Lagrangian. What we've just derived is a Hamiltonian. But if I look at the phase of wave, which is what we're working with here, we haven't said much about the quantization of the amplitude, but we have said a lot about this. That's invariant. That is really a cool invariant, a dimensionless invariant. So I replace the k, you see, with the quantities that go with it. That is, here's the k, and then there's the x. I've taken a derivative of this phase, so that's a dx dt. And then I've taken a derivative of the this part right here, dt dt. Well, that's 1, so I just get an h bar omega there. And then I go ahead and I start putting in the values for those that we've just derived. They're all listed down here at the bottom. Okay. And I also identify with momentum and energy while I'm at it. Okay, what I'm getting is the Lagrangian, px dot. This is Poincaré's relation for the Lagrangian. Okay, it's also called a Legendre transformation. Just out of curiosity, how many people are following this? I see wiggle. That's fine. That's fine. That's about as well as people know classical mechanics. Period. Because they don't know the underlying quantum mechanics that makes it happen. You see, and that's what we're getting here. The group velocity is this guy, you see. So all of this stuff can be put together in the Lagrangian to produce this very beautiful relationship. It's the secant. It's using stuff in the table, okay? It's got a minus sign. And what's really cool is the Hamiltonian, which is the thing we were derived before. That's called the energy, the total energy. It's the hyperbolic cosine. This is the inverse with a negative sign. Okay, well, that's really neat because if I use a stellar angle, then I discovered that the Lagrangian, which is a function of group velocity, uses it as a polar angle. That's the Lagrangian is this curve right here. Actually, it's this curve here without the minus sign, but with the minus sign, it's right here. And it kisses the Hamiltonian right here, and they both have the same curvature. So you're taught that the Hamiltonian Lagrangian, well, what's the difference? One of them is 1/2 mv squared, that's the Lagrangian. It uses v, which is the group velocity, we call it u here. And then there's the Hamiltonian, which is the momentum squared over 2m. But that's just, different ways of writing the same thing, isn't it? So aren't they the same thing? Well, yes, they are at low regions. But this one goes to heaven. This one goes to hell. That's a big difference, right, in Arkansas. And I hope that you enjoyed this. and want to look at some of the stuff that's waiting on the website. We've gone about 10%. We hope to go ourselves much more. And maybe you can participate in that. Okay, thank you. Any questions you want to ask, you can ask now in the presence of your peers, or you can ask it later. We'll be here for a while. Anybody think of something that they can phrase? Usually doesn't happen. Brad back there in the room is the only one that asked a question after one of these diatribes. So that's what you need to do. You have to question the axioms, but you also have to question everything anyone tells you. Everything. You have to be a police detective of the highest order to be a theorist. In any scientific field, not just this crap. This is just the infrastructure.
The police detectives are always bumbling.
Let me get closer to you because I'm a fan.
The police detectives are always bumbling around. They can never get the
Well, you're thinking of
facts.
Peter Falk.
They can never
Right.
get the facts
Right.
straight. You got to be a private investigator if you actually want to
Yeah.
figure it out.
Yeah, you can't make a big splash. You gotta be going in the back door, so to speak.
So can I ask you a question?
Yes, certainly.
So
You're the one that's working with the pseudo-relativity, which is occurring in graphene around certain points in the control panel, which is the inverse space-time.
So what you are doing is defining a metric space in a way. You are defining a matrix through those intersecting lines on the.
For just what would be normally called flat space.
That's then my question.
Yes.
So you have a reference.
Do you want to go ahead and get the curved space example, the only one we have, which would be the acceleration of, yes. And that's the one we want to look at next.
Okay.
It's really amazing that if you just ask, what does it look like if you have some kind of elevator, like Einstein proposed, that has constant gravity for the occupants. In other words, what looks like to the people a constant gravity field. What does it look like to people outside? Well, it's just the same geometry. And then the other question to ask is, what happens in transitions? What are the Feynman diagrams geometry? Okay, same answer. Every time you do a transition, you're going from one hyperbola to another. This one is staying on one particular hyperbola in space-time, but in per space-time, it's going like, it's gaining speed.
So what you're saying is all you described
That's curved.
applies to a single one.
Yeah.
And then, okay, so you are, so you are applying the transformation, so you have like a reference, say.
The rest frame would be that screen.
Yeah.
So we're sitting here watching somebody on a rocket ship that is capable of maintaining its acceleration.
You're transforming the lambdas. How does the transformation get in? How do you put the curve?
You use light, and that's what all those things are. You imagine that you have a really powerful light source on each side, and so let's say we set it up like Alice and Carla. Let's suppose that we had it at 600, 1200, and a 300. Okay, and that would cause a wave to have a velocity in there of 3/5, right? Now I start turning the knobs on the laser. If I turn them all back down to 600, now I've got a standing wave. So what this is doing is it's chirping the laser, or else it's have a whole bunch of lasers laid out that each fire in sequence to meet wherever the object is, okay? And always make sure that it sees green. So in the rest frame, they're always going to say see green, or some other color, right? If you do that, you'll get constant acceleration. And all you do is get an invariant. You have to get an invariant your trajectory, because no one's going to argue with you about what those people are feeling on their gravity meters. That's something that's written down. You see, so that's the most elementary curved space-time that I am thinking of right now. Now, the next most elementary is something to play with circles, but it's got a problem because circular waves have a lot of Fourier components. Here we're just having two. So the jury isn't in on
Necessary.
And also, this one gives you headaches if you really think about it, because you rederive all the things about gravity that say that you age more slowly in the basement than you do in the attic. And that's what you're getting here.